Okay, today we're learning about the mean value theorem. And what the mean value theorem says is that if your function is continuous on the closed interval and differentiable on the open interval, then you're guaranteed at least one spot inside that interval where the secant slope is equal to the tangent slope. So in terms of this race, let's talk about what our secant slope is and let's talk about what our tangent slope is. For our motorcycle, if you look at the total distance that you travel, in this case that was a quarter mile, and then you divide it by the total time. In this case, it took 10 seconds. That will give you the average speed, or in this case, that's kind of like our average rate of change. So that will be our secant slope. Now, as long as our function is continuous on the closed interval and differentiable on the open interval, the mean value theorem is guaranteeing that there's at least one time inside of that interval that our instantaneous rate of change, that would be like our tangent slope, is going to equal this average rate of change, which is like our secant slope. Now let's find out what this average rate of change is. In other words, let's find out what the secant slope is. Okay, in that video, you saw that we went a quarter mile in 10 seconds. Okay, now we're going to want to change that into miles per hour. We're going to simplify this and we'll start by multiplying the top and the bottom by 4. And we want to change seconds into hours. So we know that 60 seconds is the same as 1 minute. And we know 60 minutes is the same as 1 hour. Okay, we can cancel these seconds on the bottom with these seconds on the top. And we can cancel the minutes here with the minutes there. So those cancel. We can also cancel the 4 and the 1/4. This is going to give us, and that's equal to 60 over 4 is 15. 60 over 10 is 6. And miles per hour. So that's how we're getting 90 miles per hour for our average speed. Now your average speed is kind of like your secant slope. And today we're doing the mean value theorem. The mean value theorem says if your function is continuous on the closed interval and differentiable on the open interval, then there's at least one spot where the secant slope is equal to the tangent slope, somewhere inside of that interval. So our secant slope was 90 miles per hour. The tangent slope is kind of like an instantaneous rate of change or an instantaneous speed. So we're going to be able to use the mean value theorem to say that there's at least one time during that race where the motorcycle was going exactly 90 miles per hour. Now, just as a review, there was another theorem we learned about a long time ago called the intermediate value theorem. And the intermediate value theorem said that if your function was continuous on a closed interval, then you would be guaranteed all intermediate heights in between the starting height, in this case for us it was 0, and the ending height, which was 145. And that's because we started at 0, and the motorcycle ended up at 145 miles per hour. So according to the intermediate value theorem, we would be guaranteed all intermediate heights, in this case all intermediate speeds, and so 90 miles per hour is an intermediate speed. So the intermediate value theorem also guarantees that there's at least one time inside of that interval where our motorcycle was going 90 miles per hour. Okay, with our example with the Ducati and the Ferrari, if we came up with an equation for the motion, it would be continuous and differentiable everywhere, except maybe the starting point. So it would satisfy both of these conditions. But now let's take a closer look at the mean value theorem in terms of a function, an actual function. We're going to look at the first thing, which says your function must be continuous starting from A to B. So let's click on that and let's see why. Here's an example where your function is not continuous from A to B. You can see the blue line is your secant line, but there is no tangent line that would be parallel to that line. So in other words, there is no spot inside of A and B where the tangent line has the same slope as the secant line. No matter where I move this, you're not going to find a spot where the tangent line has the same slope as the secant line. So you must be continuous from the start to the end, from A to B. Let's go back. We're also saying on number 2 that it must be differentiable from A to B, but not the endpoints. Doesn't have to be the endpoints. Let's see why. Here's an example where it's not differentiable from A to B. This function is not differentiable right here, Again, that just means the derivative does not exist or the slope does not exist at that spot. And that's because the slope from the left is -1 and the slope from the right is +1. Remember, a derivative is a limit, and the limit's not the same from both sides, so we're going to say it's not differentiable at x equals 0. And you'll notice that I can move this blue tangent line anywhere I want inside here, and I'm not going to find a spot where the tangent line and the secant line have the same slope. So this is why your function must be differentiable inside of your interval from a to b. Let's go back. Now, if you satisfy these two conditions, your function is continuous on the closed interval from a to b and differentiable on the open interval from a to b, then the mean value theorem says that there exists at least one x value inside of that interval where the slope of the tangent line is equal to the slope of the secant line. So this is a good example right here. The red line is your secant line, and the blue line is your tangent line. There's at least one spot where the slope of the tangent line is equal to the slope of that red secant line. Okay, for this example, it asks how many x values satisfy the mean value theorem on the interval shown below. You can see we're starting at this point, we're ending at this point. You can clearly see that the function is continuous on that closed interval. You can see from the beginning to the end, I can draw the picture without lifting up my pencil. So that means the function is continuous on that closed interval. You can also see that the function is differentiable on the open interval because there are no spots inside here where the derivative is undefined. The mean value theorem is just an existence theorem. It just says there exists at least one spot inside this interval where the slope of the tangent line is equal to the slope of the secant line. The secant line is already drawn. As you can see, this is one spot right here where the slope of the tangent line is equal to the slope of the blue secant line. Here they're asking how many x values satisfy the mean value theorem. So how many spots does the tangent line have the same slope as the secant line? Well, there's another one down here. That would be number 2. And then there's a third one up here. That would be number 3. So this example has 3 x values that satisfy the mean value theorem. Remember, the mean value theorem is just an existence theorem. It just says that there exists at least one, but there could be more. In this case, we had 3. Final answer for this one was 3. Okay, we're going to go ahead and do this example. We know that x squared is a polynomial, so it's going to be continuous and differentiable everywhere. So that means it's continuous and differentiable from x equals 0 to x equals 2. We want to start by writing that out. We're going to say that y equals x squared is continuous and differentiable everywhere because it's a polynomial. So that means that y equals x squared is going to be continuous on our closed interval from 0 to 2. It's going to be differentiable on the open interval from 0 to 2. So you always want to start by explaining why the conditions are satisfied for the mean value theorem. Remember, it must be continuous on the closed interval and differentiable on the open interval, but you have to say why. Now, the second thing we're going to do is figure out what is the slope of the secant line. Our first point is going to be 0, 0. So I'm choosing this x value and plugging it in, and I'm getting a y value of 0. Then I'm going to plug in 2, so I'm choosing this x value and plugging it in, and I'm going to get 4. Then I can just do the slope of a line that goes through 2 points, y minus y1 over x minus x1. Okay, the slope of the secant line is 2, and I want to set that equal to the slope of my tangent line, and that's just going to be the derivative. Our derivative of x squared is 2x. And if I solve this, I'm going to be able to find the spot where it happens. Okay, we divide both sides by 2. And we get x equals 1. So x equals 1 is going to be right here on the graph. We're saying at that spot, the slope of the tangent line is going to equal the slope of the secant line. And it looks about right. Okay, we'll do another example. Again, this is another polynomial. So you want to start by saying that the function is continuous and differentiable everywhere because it's a polynomial. So that means it is going to be continuous on the closed interval from -2 to 2 and differentiable on the open interval from -2 to 2. Once you satisfy the two conditions, you're basically done with the mean value theorem. You can now say that there exists at least one spot inside that interval where the slope of the tangent line is equal to the slope of the secant line. What we're actually doing right now is we're taking it one step further and we're finding that spot. If you look at the graph right now, you're going to see we're actually going to get two answers. There's going to be one spot over here. I'm going to go ahead and circle it. And there's going to be another spot over here. There is at least one spot, but remember, there could be more. This example is going to have two spots that satisfy the mean value theorem. So that means there are two spots where the slope of the secant line and the slope of the tangent line have the same value. Okay, let's try to find those two spots. Remember, these are both x values. We're going from x equals -2 to x equals +2. So we're going to plug both of those x values in. That'll give us 2 points. Now that we have 2 points, we can do the slope of a line. It's going to be y minus y1 over x minus x1. It's going to be 8 plus 8, which is 16. And the bottom is 2 plus 2, which is 4. So we're getting 4 for the slope. Now this is the slope of that green secant line. We want to find out, is there anywhere that that's going to equal the same slope as the slope of our tangent line? Remember, the slope of your tangent line is just the derivative, so the derivative of x to the third is going to be 3x squared. You're going to have to divide both sides by 3. And then take the square root of both sides. I'm skipping a bunch of steps, but we basically get x equals plus or minus the square root of 4 over 3. Now you could simplify the square root of 4 over 3 if you wanted to, but basically those two spots are going to be right here and right here. So the mean value theorem tells us that there exists at least one spot inside that interval where the slope of the tangent line equals the slope of the secant line. But there could be more than one. In this example, we got 2 spots. Okay, now we're going to take a look at a special case of the mean value theorem. We're going to call it Rolle's theorem. Rolle's theorem, I circled the O. It's kind of like a 0. That's how I remember it. Rolle's theorem is the mean value theorem. It's just a special case of it. And it's the case when the slope of your secant line is 0. And that happens when the beginning height is the same as the ending height. You end up with a secant slope of 0. So in that case, we're guaranteeing that there's at least one spot where the slope of the tangent line is also 0. The reason why that's important is because that kind of guarantees that you're going to get a max or a min somewhere inside of that interval. Now, this is how I remember the mean value theorem and Rolle's theorem. The mean value theorem is when the slope of your secant line is slightly slanted, just like your eyebrows are when you're mean. Someone who's mean has eyebrows that are slanted. And then for the Rolle's theorem, I always remember that a roll fits right in there. So when you have Rolle's theorem, it's kind of like you have a roll underneath your tablecloth. Again, Rolle's theorem is when the slope of your secant line is 0. And that's why I sometimes put a 0 here for the O. But remember, they are the same theorem. They're both the mean value theorem. Rolle's theorem is just a special case of it when the slope of your secant line is 0. All right, let's do some practice examples.